In this video, I want to give an intuitive argument for why sometimes when you apply, and in fact usually when you apply L1 regularization, what happens is that some of your coefficients get driven to 0, whereas when you do it with an L2 regularization, that would not tend to happen. So let's say that what we're trying to do is we're trying to predict height. And the input variables that we're using are shoe size and weight. And here I'll invent the units in such a way that basically kind of S plus W is equal to H. So I'll just rescale the shoe size and the height in such a way that that's going to happen, and the weight in such a way that that's going to happen. And another thing that I'm going to say, so that's going to be, of course, approximate. Another thing that I'm going to say is that the shoe size predicts the height a lot better. So essentially, the height is equal to 2 times the shoe size, but the height is not exactly equal to 2 times the weight. So there is some variance here. So it's approximately equal, but it's not exactly equal. So I'll just write it down. So let's say that the shoe size is, if it's like 3, then we'll say that the height is definitely 6. And then the weight here, it's like approximately, right? So it's like something like 2.8 or something. And then if this is 4, then this is 8. And this is going to be, let's say, a bit of an overestimate. So this is going to be like 4.1. And then if this is, let's say, 1, then this is definitely 2. And this is, let's say, so I'm just making it up. Let's say this is like 1.3. So you can predict the height from the weight, just not as well as you can predict the height from the shoe size. Okay, so let's say that we are trying to predict height. So we're trying to set up a linear regression such that H is equal to alpha 1 times the shoe size plus alpha 2 times the weight. And you can kind of see that lots of things will work here, right? So alpha 1 equals 2, alpha 2 equals 0 would work great. But alpha 1 equals 1 and alpha 2 equals 1 would kind of work as well. So now let's see what happens when we apply regularization. So our cost function is going to be the error in the prediction, right? So the error here is going to be something like alpha 1s plus alpha 2w minus h, and that's going to be for every I, all squared. And now let's add our regularization term. So this is the cost, which means that what we want to do is we want to say, well, this is large, this is bad, and also if lambda times alpha 1 squared plus alpha 2 squared, if that's large, that's also bad. We're trying to make both this and this small at the same time. So what's going to happen if we make lambda very large? Well, we want this to be kind of as accurate as possible. So this means that we want basically alpha 1 plus alpha 2 to be kind of equal to 2, right? Because 1 plus 1 works, and 2 plus 0 works, and 0 plus 2 also kind of works. So this thing is going to guide us to this kind of constraint. What's this guy saying? This guy's saying just make both alpha 1 and alpha 2 as small as possible, right? So now, if that's the constraint, what's a good way to satisfy it? Well, if alpha 1 is 2, alpha 2 is 0, then this guy is 4. If alpha 2 is 2, alpha 1 is 0, this guy is also 4. But if this is 1 and this is 1, then the sum is just 2. So in fact, subject to this constraint, this guy is going to be as small as possible when alpha 1 is equal to alpha 2 is equal to 1. Why? Because essentially what we're saying is that the minimum of alpha 1 squared plus alpha 2 squared subject to plus alpha 2 is equal to 2, well, that's just going to be minimized at alpha 1 equals to alpha 2 is equal to 1, which is about what you'll get for a reasonable value of lambda when you're trying to minimize this thing. So, okay, now let's say that the cost is lambda alpha 1 plus the absolute value of alpha 2. Now, if alpha 1 plus alpha 2, so alpha 1 plus alpha 2, should still be 2. If alpha 1 plus alpha 2 is 2, when is this guy as small as possible? Well, it doesn't matter, because if alpha 1 plus alpha 2 is equal to 2, and they're both positive numbers, then you can trade off the magnitude of alpha 2 for the magnitude of alpha 1. It won't matter. This guy is going to stay constant. What does it mean? It means that if you're minimizing this guy, what's going to happen is, because you'll do better when you're just using the shoe size to predict height, alpha 1 is going to become 2, alpha 2 is just going to become 0, because this guy doesn't care how you trade off alpha 1 against alpha 2. This guy just wants alpha 1 plus alpha 2 to equal to 2, and for this to be as small as possible, so that'll make essentially alpha 1 be 2, alpha 2 be 0. So this is what we mean when we say that when you're using a 1 regularization, you will tend to see some coefficients driven to 0, the coefficients that correspond to features that do not predict the outcome well, and some coefficients not, for those coefficients for which you are able to predict with the corresponding features you're able to predict that well, those coefficients are going to be large.